This video is about group actions, which is section 1.7 on Dummit and Foote. I'm going to begin with the definition, so I'm going to let G be a group and A be a set. We say that G acts on A, which I will often denote by G round arrow A. So the kind of round arrow is for the action of G on A. If there is a map taking an element of G and an element of A and outputting an element of A. So I take a little G and a little A, and there's an element in A which I would call G dot A. So, an element of the group and an element of the set give us the result of the action of this element of the group on this element of the set, satisfying some axioms, so such that 1, if I have G1 and G2 in my group and A in my set, then and I act first on A by G2 and I get an element of my set, and then I act on that by G1. That's the same as if I had multiplied G1 and G2 in my group and then I had taken that product and acted on A. So this looks like the associative property of multiplication in the group, but it's not, right? So here, these two dots are group actions because once I've acted by G2 on A, this is an element of A, and now this is a group element acting on a set element, so it's a group action. On this side, though, this one is a group multiplication. And this one is a group action. So it's important to be careful to remember that even though we're using dots for everything, we don't always mean the same thing by dot. It depends what elements are on both sides of the dot. And then the second axiom is that if E is the identity of G, then E acting on A is A for all A in my set A. So the way I like to think about this is that G scrambles the elements of A, but in such a way that the group multiplication is respected, right? The structure of the group is respected by the group action. Or another way to say this is to say that this induces a group homomorphism from G into Sn, where n is the size of my set A. So how is this group homomorphism even induced? Well, first, right, you make a bijection between your set A and the set 1, 2, all the way up to n, right? If A has n elements, then you can do this by numbering. We talked about this in class on Friday. And then the elements, right, when G goes to an element of Sn, I'm going to call this little sigma G, and sigma G of 1, that is where the number where G sends 1, right? If I think of the elements of A as just the numbers 1 through n, then when G acts on the first element, I get like some other number. Well, this is the, I will say that the permutation in Sn is the permutation that sounds like 1 to whatever, and so on. Right, sigma G of 2 is wherever G sends 2, and so on. Sigma G of n is wherever G sends n. So there's 2 things to check to make sure that this is legit. The first thing is that sigma G really should belong to Sn, i.e. Sigma G is a permutation. And to make sure that sigma G is a permutation, it's enough to show that the elements, G sub 1 through G acting, sorry, not G sub 1, G dot 1 up to G dot n are exactly 1 through n in some order, right? So that every number from 1 through n appears here and appears here only once. So another way yet to say this is that this forms a bijection of 1 through n onto itself, because 1 through n is finite. To say that something is a bijection, it's enough to say that it's injective. So it is enough to show that if G acting on I is the same as G acting on J, then that meant that I was equal to J to start with, right? If I get that whenever I start with 2 different numbers, I end up with 2 different numbers, then for sure this will be a permutation, because it will be forced by cardinality reasons to also be surjective. So that's the first thing to check. And then the next thing to check is that this is a homomorphism, right? Not just that this is a well-defined map, but this is an actual group homomorphism. So check that sigma of H composed with sigma of G, this is actually a sigma of HG. And this second part can be checked using the axioms of the group action. I'm not going to do that here. So I want to say one thing about this group homomorphism, two things about this group homomorphism. Okay, so note that this homomorphism that we get from the group action might not be injective. So there could be H and G, and they're not the same element, with H dot I is the same as G dot I for all I. That's okay. 2 group elements are allowed to do exactly the same thing to the set. That's not a problem. That doesn't violate our axioms. And it might not be surjective. So if you think of the group action as being G scrambling the elements of 1 through n, and Sn as being all the different ways you can scramble the elements of 1 through n, what I'm saying is that G doesn't have to do all of the scrambling possible. It might just do some subset of this, some subgroup of the scrambling, and that's okay. Now, this homomorphism from G into Sn tells us that G, the group action, G on a set A, or on the set 1 through n, it doesn't matter how you think about it, permutes the elements of A, and composition of these permutations is the group multiplication. Okay, so that there's nothing wrong going on here. All right, so throughout, I want to make another note. Throughout, we talked about a left action. We talked about a left group action. And all I mean here is that when I write G dot A, the group element is on the left. Now, this feels cosmetic, right? I could have put the G on the other side. What would it have mattered? But this has as a consequence that the composition is read left to right. Sorry, right to left is read right to left. So let me just show it, right? So if I write H, G, A, I mean first do G, then do H, right? I think of first the action of G on A and then the action of H on that. So H, G, if that acts on A, then that would mean that G goes first and then H, because this has to be equal to H acting on GA. Okay, there is such a thing as a right action where the group elements would be on the other side of the A, and then in that case, the first element that you would do would be the closest one still. So the composition would be read left to right. It doesn't matter. We'll just take this one as the standard one, the left action, and so we'll do our compositions right to left. So I want to give 2 vocab words. So some vocab. The kernel of the group action is a priori the subset G in G, such that G dot A is A for all A in A. So this is all the elements of G that don't do anything to the set A. They don't move it in any way. This is the kernel of the homomorphism from G into Sn that we talked before, because the identity in Sn does nothing. So this is all the group elements that do nothing. And so it is a normal subgroup of G. And then the other thing is that we'll say that the action of G on A is transitive if for all A1, A2, and A, there exists G in G with G dot A1 is equal to A2. So if you think of G as scrambling the elements of A, and where the elements of A go under the action of G, transitivity means that the elements of A go everywhere. I'm not saying that every G sends every A everywhere, or that there's many G, or that there's only one G, but there's always at least one element of the group that sends any A1 to another A2. I will now do an example of of a group action that is familiar, hopefully. Dn acts on the set 1 through n if we label the vertices of the n-gon. So let's do n is equal to 4 to be very explicit. Then I know that d4 acts on the square. It's got some rotations, it's got some reflections, but if I number the vertices of the square, then I can realize a map from d4 to s4 by seeing what d4 does. So the identity of d4 does nothing, so I'm going to send it to the empty cycle. And then I can say that R is this rotation. So R in D4 would be would send 1 to 2, and then we see that 2 would go to 3, and 3 would go to 4, and 4 goes to 1 under the rotation. Our other element of D4 that we like is S. So I pick any symmetry, any reflection, sorry, to be S. So let's pick this one. So I pick S to be the one that sends 1 to 2, and 2 back to 1, and then 3 to 4, and 4 back to 3. And then I can see what everyone else in D4 does. So R squared, so this one does 2 rotations, so it sends 1 to 3. And then if we do 2 rotations, we see that 3 goes back to 1. And with 2, if we do 2 rotations, we do see that 2 goes to 4, and 4 goes back to 2. So R squared goes to 1, 3, 2, 4. R cubed is 3 rotations, so 1, 2, 3. So 1 goes to 4. If 4, we do 1, 2, 3. We see that 4 goes to 3. For 3, we do 1, 2, 3. We see that 3 goes to 2. And then with 3, if we go 1, 2, 3, we see that 2 goes back to 1. So R cubed is another rotation of order 4. And then we have our other elements, so we have SR, which should be another reflection. Now here it's important that we remember that we have a left group action, because that means that we do R first, then S. So if we do R first, 1 will go to 2, and then S will send it back to 1. So 1 is fixed by SR. 2 will go to 3 under the rotation, and then the symmetry will send it to 4. So this is 2 goes to 4. We'll see, so 4, if we have a rotation and then the reflection, 4 goes to 2. And then 3, if we do the rotation and then the reflection, we see that 3 is fixed. So SR, we knew would be a reflection, and it's the reflection to 4. SR squared is going to be first do 2 rotations, then do the reflection. So 1, we do 2 rotations, we get to 3, and then we do the reflection, we get to 4. So 1 goes to 4. We'll see 4 goes back to 1, so 2 rotations, 1, 2, but then the reflection flips you back to 1. So 1 goes to 4, 4 goes to 1. 2, we do 1, 2 rotations, and then the reflection back, so 2 goes to 3. And with 3, we do 1, 2 rotations, and then the reflection, we see that 3 goes to 2. So we only have one more element, SR cubed. So now we'll do 3 rotations, 1, 2, 3, and then the reflection. So 1 goes to 3, 3 will go back to 1, 1, 2, 3, and we do the reflection. Indeed, 3 goes back to 1. And then let's see what happens to 2. 1, 2, 3 rotations, and then the reflection. So 2 is fixed. And 4 will be fixed as well. 1, 2, 3 rotation, and then the reflection sends 4 back to itself. And I said in class that these 3 were the other 3 reflections, so now that I have them, all written down, I might as well go ahead. So I see that SR flips 2 and 4, but fix 1 and 3. So this is the reflection SR. SR squared flips 1, 4, and 2, 3. So this is SR squared. And SR cubed flips 1, 3, but doesn't touch 2, 4. So this is SR cubed. And so we can see how the rotation rotates the axis of symmetry of the reflection. If you do the same thing, which I won't because it's getting a little long, but for D3 to S3, you would get actually that D3 is isomorphic to S3. Here, I don't get that D4 is isomorphic to S4. I get an injection. This map is injective because all of the different elements of D4 are different elements of S4. That is to be expected because we define D4 to be all the different ways we can move the square. If two of them were the same, then they wouldn't be different ways to move the square. But it's not surjective, right? So the square has its own structure, and S4 doesn't care about that. So S4 would contain, for example, a 3 cycle, but D4 doesn't have any 3 cycles. There's no way for these 3 vertices to move without 4 moving and keeping a square. But if we do the same thing for D3 and S3, you can actually see that the map is injective and surjective. Injective and surjective. And it's a group homomorphism, and so it's a group isomorphism. So the last thing I want to tell you is about 3 important group actions that we'll study in greater depth later, but will start showing up right now on your qualifying exam problems. The first one is G acting on itself by left multiplication. So if the size of G is n, again, right, that just means I can number all the elements of G by 1 through n, and then the action of G acting on GI is just G multiplication by GI, which is some new element, GJ. Okay, so here for this particular group action, axiom 1 of the group action is actually just associativity because both the multiplication and the group action are multiplication. That's the only time where that's actually associativity. The map that we get G into Sn from this action is sometimes called the left regular representation of G. And it's left because I multiply on the left. There would be a right regular representation if I was focusing on right actions. Another action of G on itself is by conjugation. So this time, so I'm going to do the same thing. The cardinality of G is n, and there's, I number the elements. But this time, the action of G on GI is G inverse multiplied by GI multiplied by G. So that's what we call conjugation. So it's multiplying by the inverse on one side and multiplied by the element itself on the other side. Some people write G, GI, G inverse. It doesn't matter where you put the inverse, the isomorphic actions. So that's another important action of G. And then the last important action is if H is a subgroup of G, of index, say, D, then we get the left cosets of H. So the first one will be just H, or the identity times H, but then we'll have, 1 times h all the way to gd minus 1 times h. So that gives me d different cosets. And then I can have an action of g on one of these cosets by just saying that this is whatever coset that's given by g times gi. So that's another important group action that will come up again and again.